Okay, so here goes the wrap up for part 3 of the lab. Get everything set up here. Okay, all right, so in part 3 of the lab, what you did was you took a mass, okay, and you raised it up a certain amount until it came like this, okay? So when you started and the mass is just sitting on the table, all right, it has no energy, but by the time it gets up here, it has gravitational energy, okay? So in order to make that happen, you have to do work on it. You have to actually apply a force upward, all right, to move this mass and raise it to a certain height, okay? And we're going to assume we're raising it at a constant speed just to kind of keep it simple. Okay, so again, we're going to have a force diagram that looks like F tension, mass, hand, I guess, and then F gravity, mass, earth, all right? So without getting too complicated, okay, the earth has to be a part of this system that's storing the energy, right? Because we talked about this mass doesn't have any energy unless there's the earth, right? If I put my face under this mass, you know, out in deep space and drop it, I don't care because it's not going to fall on me because there's no, you know, appreciable gravity if I'm way, away, okay? So in the system, we have to count the earth, all right? So this force of gravity, we don't really count as doing work on it because it's within the system boundaries, okay? So the force that we are actually caring about that's doing something is this force from the hand because that force is outside of the system boundaries, okay? You don't totally have to understand that, but I just want you to know why we're using this force here, okay? So what you did, again, was you made 3 different graphs. And at this exact moment, I can't remember what the numbers were. Hold on, let me pause it so I don't confuse you. Okay, so this is going to be mass 1, distance 1, mass 2, distance 1, mass 2, distance 2, I think. Let me just double check that that was right. I don't want to confuse you. 1, 2, 2, 1, 1, 2. Is that what I did? 1, 2, 2, 1, 2. Yeah, okay. All right. Okay, so mass 1, distance 1. So the first one, let's say you used a small mass. I don't know what it was, right? Okay, and some distance, whatever it was, all right? So let's gonna say we're still graphing force here and distance here, all right? This is really the tension force, but I know that that's gonna be equal to the force of gravity because these forces are balanced. Okay, so in order to raise a mass that weighs this much, I have to apply this much tension. Okay, so we're going to think of this side as being Fg because that's how much I'm going to have to apply. Okay, all right, now these numbers might be different than yours, so I hope this isn't confusing, but we'll see. Okay, so mass 1 is going to be tied into Fg because we know that Fg equals mg. Okay, so this one we're going to say has a little force, okay, and a big distance. I'm going to do it like this. Little force and big distance, okay? And for these other ones, I'm going to say my second mass was heavier. Wondering if I should force that on you. We'll see, okay? Big distance, and then this one, we're going to do small distance. Whatever, okay? All right, and it doesn't have to be equal, but we're just kind of trying to get the idea, okay? So this one had a bigger force, but the same big distance as the last one. Okay, and then this one's going to have, again, the bigger force, but it's going to have a smaller distance. Okay, all right, so it should look kind of like this, all right? So mainly what you need to be able to say is which one of these stores more EG. Which one of these graphs stores more EG? And all I have to do is look at the area. This is like what the quiz is going to be about. Okay, so by looking at these areas, I can see clearly that this middle one stores the most energy because it has a big mass and a big distance, which is going to give it a big Fg and a big distance and a lot of area. Okay, so when I calculate this, this is a box again, base times height. Okay, so my base is going to be 0.5 meters. Okay, and then my Fg, if it's 0.5 kilograms, is going to be 5 newtons. Right, 0.5, yeah, 5 newtons. Okay, so 0.5 meters times 5 newtons is going to give me 2.5 joules. stored in this one. Okay, and then similarly, I can get the areas for this one. So this is going to be 5 and 0.2, which is what, 1? I hope. It's kind of early. I should get a calculator. Oh, joule. Okay, and then this one is going to be 2 and 0.5. Okay, so this one is still going to be 1 joule. Okay, and yours might not have 2 that came out equal. It doesn't really matter. We're just kind of trying to compare. So you should know that the biggest area stores the most energy, and in this case, for me, these 2 were equal, but yours might not have been. That's fine. Okay, but you're just trying to rank them in terms of the area. Okay, all right, now, in terms of getting the equation for this, I can start again with A equals base times height, okay, and I know the area is going to be the EG, because it's the same thing as always. When I do a force times a distance, it gives it area, and in this case, when I raised it up, it had EG. So the base is going to be the distance, and the height is going to be, and the height is going to be the FG, okay? We usually, write this, instead of distance, in this case, if it's EG, it always has to be vertical, right? Because if I slide it sideways, it didn't get any EG. It has to actually raise up. So we usually call that height, okay? Although distance isn't wrong, it's just the way we usually call it. Okay, and then instead of FG, we're going to use the equation that we know from last semester, which is the weight, which is mg. Okay, because again, even though we're applying this tension force, we know it has to be equal to however much the object weighs in order to raise it at a constant speed. Okay, all right, and then if we just reorganize that slightly, we'll call it mgh, which is how we usually write the equation. This is usually the way that you'll see it. Okay. Right? So in order to get more EG, okay, the object either needs to be more massive, right? Or technically way more because, right, if it's on the Earth, it's going to be different. I'm not as scared if I drop something on my hand on the moon because it's not falling as fast, okay? And the higher I raise it, the more EG it's going to get, okay? All right, so let me look at the document. Okay, so never mind. I think that was all that was asked in the CER. So this one's done.